So how many of you are coming for the first time? Okay, so maybe more than 90%. So welcome you all to the Sci-Tech lecture series we organize here in IIT Delhi. And this is the first lecture for the year 2025. And the objective of this lecture is to just to introduce you a bit to the field and maybe tell you a little bit about what kind of research is going on in this particular field in IIT Delhi. And myself, Rahul Mishra, by the way. And today's speaker, we have Professor Ritabrata Thakur. He is from the Applied Mechanics Department here in IIT Delhi. He is assistant professor. Before coming here, he did his postdoc from University of Michigan in USA. And his PhD is from TIFR, Tata Institute of Fundamental Research in Bangalore. His research interest is basically fluid dynamics and especially concerning to ocean and atmosphere. So that's what he's going to talk about this in the next 45 minutes, 1 hour or so. Okay, so I think the mode of this lecture he will be going through his content, but I think they can ask question anytime. Okay, so anytime anyone has any doubt, just raise hand and make this session interactive. Okay, so let's welcome Prof. Ritabrata.
Thank you, Professor Mishra. Thank you, everyone. So, I hope I'm audible to everyone towards the end of the video. So, thanks for joining, thanks for coming here. You're welcome to IIT Delhi. And so, this is the first talk of this kind of outreach series that we do for people who are moving on to doing higher studies, who are interested in science, and give them exposure to various things. I mean, it's not possible to talk about everything, but at least the few things that we can develop. So I am, as Professor Mishra said, so I am an assistant professor in the Department of Applied Mechanics. My name is Ritabrata Thakur. So I have a background in engineering and degrees in engineering and physics. So I work in basically in the area of fluid mechanics. But just to get an idea of the demographics, so how many of you are from the lowest class? I mean, from the 9th standard, 8th standard, is the lowest? Yeah. 9th standard. So, from this school, everyone is from 9th standard. And how many of you are from 12th standard? 11th? Okay. So people in 9 and 11 share things, so you might understand the things that you have learned in 9, you are understanding some advanced things of the same topics in 11 that people from class standard 8 share with 10 and 12. So you have probably, you probably know the difference between a solid and a fluid, right? But that's by intuition you can tell that, let's say the desk you are sitting in is a solid, whereas the air that you are breathing is fluid, or the water that you drink every day is fluid. And probably this might be an appropriate question for the 11th standard. As we discussed earlier, so I want this to be interactive. So please feel free to ask any question at any point if you don't understand. And then we'll try to break it down to as simple a concept as possible. So, what does the difference come to your mind when you think about the solid versus fluid? I don't need something from the textbook, but how do you feel about it? What's the difference? Yeah.
Basically, solid is the particles that the solid constitutes of particles which are closely. So basically,
You can sit down and speak. No.
okay. So solids, the particles of a solid are closely binded together, whereas fluids are loosely packed.
Yeah, that's a good definition. That's a good first order definition. So the solid has the the constituent elements that's constituting the solid, that's creating that solid object is more organized, more tightly packed as compared to, let's say, a fluid element. So water has, so it's the same element can have both solid and liquid properties. The best example is water. Right? So you have, when you freeze water, you get a solid form, which is ice. And then when you heat it, in the room temperature, you get something which is fluid. And you can imagine that, let's say, you're trying to push your desk, and you're trying to force which is parallel to the desk. Let's say this is the surface of the desk, and you are trying to put the force which is parallel to the desk. You see that the whole system actually, at least according to your eyes, it remains stable, even though there are small microscopic changes that can happen. But to the human eye or the person who is doing it in our lens scales and time scale, this remains stable. Whereas, let's say there is a drop of fluid, and you are trying to push it this way, and you see that it cannot resist that force. So it actually takes, it actually changes the shape in the direction where we are putting the force. Okay. So and there's a whole field of study regarding how these solids and fluids actually differ, what are their properties, and what is the dynamics. So dynamics means how they evolve, how they change when you have when you put some force. So when you put some force, the way they change is what constitutes the dynamics. And the field of study that constitutes how a fluid changes its shape, how it responds to some kind of a force, be it a mechanical force, be it an electrical force, or be it magnetic, is the area of fluid mechanics or fluid dynamics. Okay, and if you move one step further, you can apply these concepts of fluid mechanics. Whatever you understand from the governing equations of fluid, you can apply it to fluids around us. Okay, that means water or air that we always breathe, and water that we always drink. And one of the biggest source of water on Earth are the oceans. Okay. So today, again, this is an interactive talk. Please talk to me whenever you feel there are any things that you need to clarify. If you had any doubts before coming here, when you saw the title. So I don't have any set number of slides to finish, but I just want you to understand the things that at least we end up discussing. So in these slides, I'll try to briefly describe the things from the point of view of what I have been exposed to during my research work. So this constitutes understanding the ocean, which is, for my case, it was primarily in the Bay of Bengal. So we went out into the ocean, and how many of you have seen the ocean actually? Because when you've gone to the beach, you've seen the ocean, right? So yeah, so we started off from Chennai. We went on a ship, which is a research vessel. We went to the middle of the ocean for one time for 21 days and second time for about a month, and we go and collect data. And that is one aspect of my research, and I'll tell you the other aspects, for example, how to get data from satellites and just by putting some instruments in the ocean. However, we probably always don't appreciate the importance of oceans in our lives. So this is what this overview slide tells us. This is giving you some numbers, but just by which shows that how important the oceans are actually for our survival. So first of all, they contain, as I said, most of the water on Earth. Earth's surface is covered in oceans. So almost more than 95%. So these are some average numbers. Do not take it by heart, and exactly it's 97%. Like changes, so it's approximately 97% of total water on Earth is ocean. And you might have always heard, right? 70% of the Earth's surface is covered by oceans. Okay? So only the rest of the 30%, we human beings and approximately 85% of the global evaporation. So almost all the rain that you feel, so the next time you feel the rain, you see the rain coming. So please imagine that most of the water that comes down as rain on Earth has actually originated in the oceans at some point. So ocean actually, so we have sun, so there's heat coming into the Earth, and it's heating. And what happens when you heat water? So the process is called evaporation. So the water evaporates into, it changes into vapor form. So there's a phase change happening. So it changes into vapor form, it goes up, and then it creates, it undergoes various things. So it nucleates over some particles, and then it forms clouds, and then it condenses, and again comes back to Earth as well. Okay. So this actually, so when water goes up and it condenses, it releases some kind of heat, because actually to become vapor form, it actually gains some energy. And then when it condenses again to liquid form, it releases that energy. So it's called latent heat of condensation. So there's a source of heat. That means when the condensation happens, there's a source of heat. And when there's a source of heat, you know you can drive motions. For example, if you heat air in some section of the land, cold air from other section will come into fusion because the warm air actually rises. So this, so all the rain we get across starts from at some point in the ocean, and it actually produces a lot of the planet's oxygen. Can you think of the organisms that might produce oxygen in the ocean? Do you know the term? People from 11th standard, yeah, phytoplankton. So these are phytoplanktons which are in the ocean, and these are tiny organisms, centimeter scale, sometimes micro scale, which actually does photosynthesis, and exactly like plants, they take up carbon dioxide and they produce oxygen as a byproduct. And by many estimates, this is insanely high percentage of oxygen which they produce. And there's a huge amount of life form in the ocean. Okay, and most of the big fraction of the oxygen that is produced by phytoplanktons is consumed by those organisms, and it also leaves appreciable fraction for the rest of the organisms on land, so humans and other animals. There's also a lot of exchanges that's happening between the ocean and the atmosphere. Okay, so here is an image of the east coast of the United States of America, and this is showing you the color of the. So the color is showing you the temperature of the ocean at a certain instant in time. Okay, so taken from satellite and then put into model, so you get some kind of approximate image like this. And you can see that there is a section in red and there is a section in, so the red is is higher temperature while the blue is lower temperature. So you can see that there is always, I'll show you different videos, you will always see that there is a temperature difference in waters from different parts of the ocean. Okay? And this is one of the forcing which drives various different motions in the ocean. And you will see that there are various small scales. Even in this still photograph, you can see some bigger scales, there are these smaller scales, and there are these other smaller scales that happens here. So because of these kind of motions, there is constant evaporation going on because when the ocean is heated, and then there is precipitation, there is condensation of water vapor from the atmosphere of the ocean. So the ocean is constantly interacting with the atmosphere. So it's not staying still as a different entity. So it's an incredibly important component of the whole the biosphere that we live in. And it actually contains a lot of heat. So denser as compared to reality. Okay, so this is the reason why a few meters of the ocean. So imagine ocean depth of will not even this full height, even half the height of this room contains as much heat as the whole atmosphere above, which is of tens of kilometers. So you can imagine how much heat the ocean can accommodate. And if something goes wrong in the natural process of the operation of the ocean, then it creates various issues, including changes in local weather and long-term climate changes. So, and because this heat is actually distributed, this actually makes the places habitable. So most of the heat is actually concentrated. So from the sun, the tropical areas are the ones which mostly get the heat. And because this ocean is in constant motion, this heat is being carried outwards towards the northern and southern areas. And this redistribution of heat, that is taking away heat from the tropics to the higher latitudes, actually makes the places in the upper latitudes habitable. So it's more conducive for survival of humans. So if this was not so, then most of the people would have been concentrated around the equator, or at least not very far from it. But so just by the numbers, we know that this is an incredibly important phenomenon. Incredibly important part of the ecosystem. But there is also actually something which, in recent times, that we have heard this word called climate change. Have you heard of this term somewhere? At least some of you. So you have heard of climate change. So what do you mean by climate change? Yeah, that's a good explanation. I mean, it's a very important point to understand. So as the graph shows, the average temperature of the Earth in the modern human era has increased above a certain critical limit, which is calculated based on some pre-industrial level measurements. Okay. So you know that during Industrial Revolution, you might have learned it in your social sciences. Industrial Revolution, we had a lot of industry coming up in different parts of the world, and they started producing lots of mass-produced goods. And this, because there's a lot of fuel consumption, so we released a lot of carbon dioxide into the atmosphere. Okay, so we unknowingly did something which was not natural. We did something which was not the natural trend of how the Earth was evolving. So actually, that has led to something which is a bit concerning, in the sense that the temperature actually has, in this year 2024, was the warmest year on record. So it has crossed the 1.5 degrees centigrade threshold above the pre-industrial level. And this was also partly driven by a phenomenon in the ocean, and this is called, and the phenomenon is called the El Nino. I don't know if you've heard of this term called El Nino. Okay. So El Nino, we'll also describe what El Nino means. So combined with human heat input into the atmosphere, and also the El Nino happening for the last few years. So this year was modest on record. And because this ocean is a huge important component of this whole ecosystem, something that changes in the ocean is a marker that something is happening with the climate. And the changing ocean actually leads to something very drastic. Okay, for example, in this case, we know that because the ocean has warmed a lot, this has consequences to methane. So if you recall, I mean, just imagine you are heating some ice in a bucket, so it will start melting. So this figure is showing you um, the Antarctic sea ice distribution. Okay, and I'll tell you one by one what this everything is. So this is the Antarctic ice shelf. So this is the ice sheet and the ice shelf, and this yellow line, this yellow curve actually gives you an average of the total sea ice that was there in this period, 1980 to 2010. Okay, this 30-year period, there was this amount of ice, this yellow line. Whereas on this day, that is, I think this is in the Monday, this is September 19th. So the sea ice cover is actually much lesser than this yellow, so this cover that you see. Okay, and the amount, and it seems actually pretty less by this figure because we are not putting a scale here. But just to give you an estimate, so this reduction is approximately 1.5 million square kilometer, and this is 5 times the size of the United Kingdom. Okay, so this is very drastic. This has never happened before, at least in the recorded human history. And there is strong reasons to believe that due to warming of the oceans and the warming of the climate, that again affects the ocean, this kind of a sea ice loss has happened. And if everything, all the ice melts in the Antarctic, so the whole sea, like the Earth's sea level approximately goes up by 60 meters. So you can imagine how deep our oceans will be and how the coastal areas, most of the low-lying areas will be. So this is the same with Arctic sea ice. So this is the median, and the color, so this, I mean, this is the median for this 30-year period, whereas this color shows you the current, that is in one day, 11th of September, the sea ice cover in the sea. So again, this is one of the historic lows. Similarly, is the case with Antarctic sea ice. And we humans actually have knowingly, unknowingly, willingly, unwillingly have done damages to the ocean in terms of pollution, in terms of changing its natural state. So, because of a lot of plastics have to go through your drainage system and they end up moving to the ocean at the end. There's a lot of plastic pollution, and there is a lot of microplastics in the ocean. I don't know if you have come across this term reading some newspaper articles that we seeing it. So there is a big concern about microplastics polluting the water around us. Okay, and it's now, like very recently, not even a month ago, it has been realized that this has actually gone into human bodies, even in human reproductive systems, organs. These microplastics have been actually formed. So this does not seem natural. Okay, so we don't know what is the effect of such kind of pollution that is actually going into us, and what probably will be their effect. And also because a lot of chemicals, but a lot of fertilizers and pesticides actually make their way into the ocean, it actually leads to uncontrolled growth of algae blooms in some places, and this leads to depletion of oxygen available for other marine organisms. For example, this shows some fishes which died and were driven to the shore. So this was because of a thing called hypoxia. So there's a loss of reduced amount of oxygen in ocean water. this actually brings us to the next step, that we don't know what is going to happen with the ocean unless we start observing the ocean, unless we start studying the ocean. And if you recall, on the first slide I said that ocean is fluid and the study of those is fluid mechanics. So we combine understandings that we obtain by looking at the ocean, by gathering data by various means that I'll show you shortly, and then using some theoretical tools to understand the basics of those phenomena. Okay, so it will probably have some importance in the long term, where we are trying to inculcate those things into the large-scale models or large-scale simulations of ocean that we run. Okay, so nowadays computers are big enough to do simulations of ocean. That means you have the you write a solver or a code which takes into account all the forces that's happening that are occurring in the ocean, and you allow those and you allow the fluid to evolve under those conditions. And you put appropriate boundary conditions, that is, you put lands and ice, and you see how the ocean evolves in those conditions. So the ocean is constantly in motion, as I told you earlier. There are various forces that act on the ocean, and there is actually a very interesting force which you always feel. And do you know what force is that on the ocean? Yeah. So that's a nice addition to this. There is Coriolis force because of the fact that the ocean is, so the Earth is actually the non-rotating, it's a non-rotating frame. Okay. So that means it's not an inertial frame of reference. So because it is not an inertial frame of reference, you have Coriolis force that comes into it, and then there's centripetal acceleration, a centripetal force, which you can do some editing. But that's a very interesting force. That's a very interesting force. But something which is driven by some outer bodies, and you feel. Yeah, exactly. So very good. So this is the other force is called the tidal force, which is driven due to the gravitational pull of the difference in the gravitational pull of the sun and the moon. Okay, and so it pulls. So you know that there are two bodies. Whether you can see it or not, they have some attraction between them. Okay, right? So it pulls, both of these pull each other. And sun is extremely massive. The moon is smaller, but it's also nearer. So if you have huge distance, it can actually compete with the force that's generated by an extremely huge body, which is very far. Okay? So there is a difference in the gravitational attraction of the sun and the moon, and this actually pulls the Earth into the direction where the gravitational pull is maximum. In different seasons, it changes with season, and it's actually also pulling us. Okay, it's pulling the solid Earth too. It's not that it's just pulling the water on the Earth, but we see the water as being more dynamic, it's being more non-resistive to forces. We can see that it's moving, but actually the solid Earth is also pulled, and there's also a slight motion of centimeter scales on solid Earth. So there are various forces, including the Coriolis force, and then we have the tidal force that acts on the oceans, and these lead to various kinds of motion. I'll just show you one example. I'll open the high quality video. So this is a video developed by NASA, and this is showing you the ocean currents. So this is what you saw initially. This is called the Gulf Stream around the east coast of US. And you can see, when I told you that there are various scales of motion, you can see this is a big current, almost straight line in different sections. And there are these rotating motions that happen, which are various scales. There's a bigger rotating motion, there's a smaller rotating motion, and there is this equator where there is a strong velocity flow this way. And there are these interesting cyclonic features that actually happen. So this is the east coast of Africa, and this is called the Agulhas current. And then again we move from Africa to the Indian subcontinent, and this has interesting vertical features or rotating features as you saw in other parts of the ocean. So this is to give you an overview, at least make you appreciate that the ocean is constantly in motion. There are various things in the ocean that there's various flows in the ocean that actually make it dynamics and it's dynamical. And then all of these motions can actually be reproduced in our small scale studies, that is using computers or using some modeling and things like that. Okay, so I'll briefly stop for a minute or two to ask you if you have any questions, any doubts in these things. The question could be anything, so feel free to ask anything that you want. Yeah.
Sir, how does the lack of oxygen affect the fish, or how does it happen?
Yeah, once you release a lot of nutrients and fertilizers into the ocean, this leads to excessive growth of algae, okay, excessive growth of organisms which actually can use those nutrients and then grow. So you're changing the natural balance. So there is no a balance between, so I mean in the way you change this system altogether. So they grow much and then it starts, so all these, then they start consuming oxygen. They start taking up at least some of the organisms that grow due to the excessive nutrients. They start consuming oxygen and it reduces oxygen again to form the other marine organisms.
Sir, so you showed the video in which the current pattern was being shown. So is this been constant for a long time or does it change over time? If so, what are the factors which affect the change of pattern of ocean currents?
Okay, so that's a good question, and there are various things which change the pattern of ocean currents. The first part of the answer, the first part, so it's no, it's not constant, it changes over time, and the time scales are even from seconds to hours to days, so there are different ways in which the oceans can change. So it's not constant, it's always moving, it's always distributing heat and salt that's there in the ocean, nutrients. So it's redistributing everything. And there are various forces. For example, one of the forces that she mentioned is the tidal force, which creates flow. So it creates tidal currents that actually leads to these kind of flows. And there is wind flowing over the ocean, which also generates surface currents and other internal currents that we'll see soon. Okay. So these tidal currents, which are generated due to tides, they move over the ocean floor, and you know that the ocean floor is not flat, right? So there are hills and valleys in the ocean, and when they move over those kind of disturbances, there are various other motions that are generated, and we'll see a video about that. Yeah. That's a good question. That's a good research question. How exactly they affect us, they harm us. But to give you a definition, microplastics is exactly what it means is. Okay, it's a microscopic remnants of plastics. So we have single-use plastics, and those can break down into very small things, and they are invisible to the naked eye. And then you can drink water with microplastic pollution, or the organisms in the ocean can drink that, and then how it affects is yet to be seen, in the sense that we have never had this thing earlier. So unless you have some evidence of something happening over long term, so I don't think I make a speculation here. But certainly, if something is non-degradable by the human body, it's probably not going to do anything good. So that's my understanding. Okay, so we'll move ahead. So we saw and there's a nice question about what are the kinds of forces. And so this motion is actually forced in various scales, and it leads to various different kinds of flows. And one of the most important flows is, which happens on very long time scale, is the thermohaline circulation. So this is, you don't have to worry about all the terms. I'll just briefly tell you what this is happening, what's the basics of it. So because when you heat water, or this heat input into the water, its density decreases. And when you cool the parcel of water, its density increases. So it has to, if there is a configuration where you heat water on top, you cool water on top, then it has to sink down because it is heavy and it has to go down. So the same basic phenomena actually happens in this. Yeah. Again, that's a good question. I think it's a very good question. People are looking into the ways in which you can naturally degrade those microplastics. But the thing is, it just comes to the molecular shape of what constitutes the plastic, single-use plastic molecules. I'm not sure if they can be degraded by bacteria into just primary elements. Okay. So these are very interesting questions regarding microplastics. So this actually happens in the order of 1,000-year time scale. Okay, so if there is a parcel of fluid starting somewhere here, for it to approximately come back to the same place, it takes about 1,000 years. So it goes in. So this is the flow. This direction shows the flow, and it goes to the areas where it's. So this area is cold, right? So these are the poles, and these areas are cold. And you can see that there is something called deep water formation. So you don't have to be confused in all the terms. I'm just telling you the basic thing. So I just focus here. So if it's cold, it's heavier, and it has to fall down. It has to go down. Okay. So if there's cooling happening here, and it falls down, and this again is coming down in this direction by these arrows, as you can see here, the things that I'm pointing to. Okay, this is coming down as the blue line. So it's coming down as the blue line, whereas it went through, it went into it as a red line, which is higher temperature, and this is the surface flow. And here it cools down, and this blue line is showing you the deep ocean flow. And there's a surface flow which is created by the winds that are acting on it. There are other forces, for example, the tidal force. And this is actually slightly hotter area because the sun is heating up the area constantly, and this warm water is produced. And these colors, green and blue, show you the areas where there are higher salt concentrations, and these areas show you lower salt concentration. So there are various kinds of salts which are dissolved in ocean water. And if you have somehow tasted ocean water, if you are on a beach, if you have tasted ocean water, taste is salty, right? So that's the salinity thing that we are talking about. So it's a thermohaline, that means it's driven by thermal gradients and also salinity. Okay, so if you add salt to your water, it becomes denser. Similar things happens when you cool water. So when you cool water, it becomes denser. When you add salt, it becomes denser. So this is this circulation, this kind of circulation is forced by thermal gradients and haline gradients. So haline gradients is salt gradients. Okay. And this again goes back to one of the questions that I was answering. So you asked what are the kinds of structures. So there are various structures, and we again should not go into detail. So I'll just tell you a brief overview of what this means. So the ocean has scales which ranges from very small centimeter scale motions to this very large scale thermohaline circulation that I showed you. These are thousands of kilometers of length. Whereas if you remember the video, we had some very small tiny scale motions too. Okay, so this graph is actually telling you, so this is giving you the length scale, okay, how big the systems are. And this is giving you, the y-axis is giving you the time scale, okay. So time scale meaning in how frequently the system changes, or how frequently there is a possibility of that system recurring, okay, and or maybe how long do they exist. For example, let's say, so I think some of you mentioned that you have heard this term called El Nino. Okay, so El Nino is what? Can someone tell me? Yeah.
Warm currents.
It is warm current, but which place? There is a specific area where it should be warm for it to be called El Nino. Again, near the equator is fine because there will always be warm currents because the sun is heating there. Yeah, that's a good answer. So it's near the west coast of Africa, US, where there is warm water which accumulates because of the fact that trade winds, which are actually a system of winds on Earth, actually slows down. Yeah. Huh? What? Yeah. Okay. Yeah. So I mean, the warm current is talking about the current. Just the basic phenomenon. Okay, this is heating at some place. There's a trade wind which slows down, and that's the reason the warm water cannot be transported from the west coast towards the eastern. From the west coast of US towards the Asia. Okay? So then this warm water heats up. I mean, this warm water stays there, and because of that reason, there is actually this affects the local weather, and in a very complicated way. In an indirect way, it also affects the Indian monsoon also. So there are various things that happens, as you can see in this length scale and time scale. So one is in thousands of kilometers scale, and this happens in time scales of years. Whereas there are various phenomena. For example, this tidal flows, that is internal and surface tides. So I again tell you what they mean. So this, you remember she told you about the tidal force. There is a force, there has to be some kind of a motion. Okay. So there are waves that moves over the surface, there are waves that move interior to the ocean, and one of them is called surface tide, one of them is called internal tides. Internal tides can be somewhere between kilometer scale to 100 kilometers, and they change in a time scale of day, whereas surface tides are bigger than that, 100 kilometers to 1000 kilometers, and they change in time scale of day. And these are actually very well-defined time scale. They are very well-defined time scale because our rotation speed and revolution is actually very precise. And there is something called turbulence that happens at very small time scales in the ocean, very small time scales. And this is, and turbulence, so we'll see that this means actually, this is a chaotic motion of the fluid. Okay. So if you remember those videos, we had that circular motion, which is causing lots of smaller circular motions further, and then it's dissipating. So this kind of chaotic motion actually is studied within the branch of fluid mechanics, and this is called turbulence. And as I mentioned here, this is beyond the spatial scale. This is much smaller than the meter scale. That's much smaller than hours. So it can happen in time scales of minutes, and it can happen in time scales of meters. Yeah, even centimeters. So, give you an overview of the kinds of ways we understand ocean, we observe ocean. So one is, one very powerful technique is satellite altimetry. So altimetry is the science of understanding the height. Okay. So there is satellites, which are hundreds of kilometers in the Earth's orbit. It goes down, it comes up, and by measuring the differences in the way or measuring the time that it takes for it to go out and come back is how you can reduce the height of the sea surface. There are various other things that goes on, but this is one of the most simple understanding. Okay, and historically, satellite altimetry has actually revolutionized the understanding of our oceans. So starting from this, one of the first satellites that was launched in 1978. So most of these are launched by NASA in collaboration with CNES, the agency in France. And CSAT was launched in 78, Topics for Science mission in 1990s. And then there were a few advanced satellites which were launched in the 2000s, which were called JSON. And then very recently, approximately 2 years ago, the satellite called Surface Water and Ocean Topography was launched by NASA and CNES. And this was a quantum leap in satellite altimetry. Okay. In all of these satellites that were there till now, they were measuring data only at a single point because there was one altimeter. Whereas this one, you can see there are two arms that spread out from there, and combined with the satellite, the altimeter which is here, they can measure actually two-dimensional data from the ocean. Okay, and we'll see how they do it. So this, apart from an altimeter, this has radar interferometer, which helps you get two-dimensional data from the ocean. This is actually a big leap in what we have been doing till now. We're just getting data from a single location by going over it again and again. If it's a repeating orbit or if it's a non-repeating, we get it at different points, and that means different time. Let's say there's a measurement at this point, and then the satellite takes some time to come back to this, so we take some certain intervals. Whereas this one, this SWAT satellite, actually is something which will give you a two-dimensional data. Okay, this gives you much clearer image of the ocean dynamics. So we'll see a video that, okay, so before that, this is how this SWAT satellite moves across the Earth. So as you can see, there is this time going here, and this color is showing you some velocity. So don't care about this geo thing, it's a geostrophic velocity, but this is the velocity of the surface currents. And this is day 2, and then you will see approximately at around day 10, it will start again repeating, coming back to the same location. Okay. So this is, as you can see, this is an organized motion around the Earth, and this is, and the reason why this is doing it is because it's trying to cover all the parts of the Earth. And because there is a certain inclination, which is not 90 degrees, so it's not covering the poles. You can see also there is no data from here. So you can see this is 7 days, and then approximately at day 10 it will start covering. It will have covered the whole Earth. So it has covered the whole Earth, and it is trying to take again measurements, which is just decides it, and it will continue doing that. So, and over time, as things should be, the altimetry has actually changed the way we observe the ocean. So this was the this is a comparison. So this video, as it progresses in time, will show you the differences in the measurements taken by the first satellites and the most recent satellite, that's SWAT. And you can see the way we start resolving, we start understanding the very small scale creatures. And this was the first measurements that was done, and this time is progressing. So this is the GeoSat mission. this is the Topics Poseidon and the Jason missions in 1990s. This is the SWOT mission, that's the most recent one. And you can see, let's say for example, if we stop somewhere around here, okay? So you can imagine, you can even look at the differences between the way we're getting the small scales as compared to which was there in the previous altimeter missions. So here the resolution was not very high. I don't know if the projection is working perfectly, but this, for example, let's focus here. You can see that these were very hazy pictures, whereas the current vision, that is the SWOT vision, has given you some structures which are very small. So these are order of kilometer scale, unlike the previous ones which were of tens to approximately hundreds of kilometers. There is a different way to, and it's an interesting way, I mentioned to you earlier. So you observe the ocean remotely, okay? So this observation using satellite is called remote sensing, because you're understanding you're sensing something remotely. But you can also do some experiments in the ocean. So you go out into the ocean. So this is a cruise ship of India, and this is called Sagar Kenya. And it's not like passenger ships where it's or cargo ships which are used for transporting passengers and cargo, but this is a research vessel. It's called the Oceanic Research Vessel, or ORV, and this ship has placed for approximately 60 people, including the crew of the ship who is actually driving the ship and doing all the things. And there's a team of scientists and engineers who board the ship along with them, and they go out into the ocean and they collect data, different kinds of data that we'll soon see. And this is the track that we actually follow. Okay, we started from Chennai. There was a stop at this location because we had to recover something. I'll show you what we did. And then we went to this location too, and then we went here, and then we took this path, and then we came back via this route back to Chennai. It's approximately took us 21 days. And this was a collaboration with the United States of America. So they also had a ship which came to India, and that was a few years later that we went also in that ship to collect data. And the reason why we collect data is, of course, satellite, you can imagine, cannot give us data from within the ocean, right? It just gives you the surface velocities. As you saw, it's giving you a surface picture. It will give you the surface height, it will give you the surface velocities, temperature, salinity, but we know the ocean is more than that. The ocean has a structure which is deeper, that means it's variable, meaning it's not a constant block. It's not like if the surface temperature is 20 degrees, it's not that the whole ocean is 20 degrees, okay? So it varies, and we need to understand what happens in the deeper ocean also. So that's the reason why we do these kind of missions. We go into the ocean to collect data, and then we deploy a few things in the ocean, which stays there for a year or a year and a half, depending on how long the batteries can last of the instruments, and then we again go back and collect those instruments, so that it saves money, so that you don't keep on doing the same thing. You don't have to take a ship, because this is a costly affair. It's actually cost you thousands of dollars to get out from, use this project, burn fuel. It's also not very planet sensitive. So you go and deploy instruments. And this is one picture that I took in one of my research tools. Okay, so this is the US ship that I was telling about. This is the Oceanic Research Vessel called Sally Ride. If you don't know who was Sally Ride, you should go and check. She is a great scientist. It's named after her. So, and these are the people, this team of scientists and engineers who are trying to recover this instrument. And as you can see, this is very exciting. You are literally at the edge, trying to pull these instruments. There is a pulley which is helping you pull these instruments, and this instrument, this system is called a mooring. Okay, so as I said in this title, this is an ocean mooring. Okay, and some examples of this is like this, and this consists of this system which floats. So this is a schematic. This is a rough schematic of this. So there is a system. This is a floating body. So it has lighter density than water, and it floats. And there are various instruments here. As you can see, these instrument measures atmospheric conditions. Okay, they are above the ocean surface. Whereas there are various instruments which are attached to a chain which is attached to this floating body. Okay, let's draw in this schematic. So there is a floating body, and there is a chain below it which has lots of instruments, and we see some instruments there. And they measure various quantities. For example, I said the temperature of the ocean is varying, the salinity of the ocean is varying, the velocities are varying, there is turbulence in the ocean, and then again there was this question about dissolved oxygen, and then there are some things where people also study how much light is going into different sections, different depths of the ocean. So this is a very rough schematic of what happens, and we went out into the ocean and we recovered this after 1 year. So once you recover all the instruments, you can use those instruments, go to your lab, recover those data, copy those data in your computer, and you can spread out across different people who are interested in various things. Let's say someone is interested in biology, someone is interested in light, someone is interested in understanding the temperature distribution or other aspects of fluid mechanics. And then you can do your own thing. So these are huge $1 million projects that are funded by governments directly. And these were collaborative efforts by the Indian and the US governments. So this was one of the photos from the Bay of Bengal. So earlier photo was also from the Bay of Bengal, but from the American ship. This is a photo from the Indian ship, Sagar Kenya. And this inflatable boat has been is deployed because this person was going and he was checking this instrument. I mean, this was again in the middle of the ocean. So these people went in, and this is the scale of the system. As you can see, there's a human being standing here, and this is probably a few meters high, and this diameter is probably 1.5 to 2 meters. So this is one of the interesting photos that I felt shows you how we humans actually are trying to understand just by going into the ocean and doing things that actually does not seem very simple. So this is showing you the deployment and recovery, and one of the experiments working. So this one is where this person, so this is a person, and you can see this is raining. He is holding an instrument. So this again, this is so you have these instruments which you have deployed in the ocean, okay? And it remains fixed because there is a huge anchor in the bottom. There is a big dead weight where you put it at the bottom of the ocean, so it approximately remains fixed. It might change a meter or so because of the waves, but it will remain fixed. Whereas, what do you do if you want to get some distribution? Let's say you want to get an idea of how the temperature varies in the bottom of the ocean, in the deeper ocean, not the bottom, in the deeper ocean, but as you change, as you move around, okay? So this is an instrument that does exactly that. So you can see this is the size of this instrument, about 1 meter length. And there are these equipments which control this instrument. And what he will do is, he will throw this instrument into the ocean. The ship is moving, ship is not stationary. He will throw the instrument into the ocean. As it goes down, because it's denser than water, it will fall. And as it goes down, there are instruments in in that ocean, in the system itself, in the instrument, which will measure different properties, including temperature and salinity. So you will see that this person actually, so the camera was fixed, and it's also shaking because the motion. As you can see, this is the kind of swell and this is the kind of wave that people have feel at some point. And this is just the Bay of Bengal. So if you go to the northern ocean, the swells are like meters and meters of meters high. So this person, it's controlling with this electronic controller how deep it can go, and then he will start recovering the instrument. And then at some point, the camera, I think, falls down because of the waves shaking. So the camera falls down and the experiment still keeps on happening. So this interestingly keeps on happening 24 hours. So once you are in the ocean, you cannot lose any amount of time because you're of course spending tons and tons of money to go there. So you want to maximize your use. So every person a group of people were given different kinds of shifts. So you wake up at 3 and then you sleep at 5 or 6 p.m. and then again someone who wakes up at the time, the group of people who wakes up at the time does this job. So it has to continuously go on for 24 hours. There is no stopping of these experiments. So whether it's night or day, raining or not, so these experiments keep on happening. And this is this is a video of something that's being pulled out of the ocean. And you can see this is an instrument that has various components. So this is being pulled out of the ocean. This can measure temperature. This also collects a sample of water. And there is this arm that's there in the ship. So all of these scientific, these arms and other various scientific tools will not be available in a normal passenger ship, but these special classes of research vessel has these. So this is being taken out from the ocean, and you'll see in the next video, I think, it's taken out from the ocean and it's placed here. So we learned that we can observe the ocean using satellites, the surface of the ocean. We now have an idea that we understand deeper ocean by these instruments, where a person will be operating probably, or there is something which is you put it there in the ocean for 1 year, which has various instruments at various depths that collects the data. Or there are ships where you can go and you can also collect some data using those. And what do you actually get from those? What's the purpose of that? It's because the ocean is actually always moving. And there is something, if you remember in that slide that I showed you lots of different figures, different names. You remember there's something called tides, right? Internal tides and surface tides. And I told you, surface tides are the motions that happen, that vary in the surface. So the interior portion of the ocean is also not stationary. Okay? So this is an artist rendering of how the internal tide looks like. And as I mentioned again in one of the earlier comments, the ocean is not flat. Okay? There are lots of hills and valleys that are there in the ocean. And because of this interesting force called magnet force, there's a current, there are flows generated in the ocean. And once they move over these topographical features, that is, all these hills and valleys, which are called topographical features, they generate waves that radiate outwards. And there's an interesting component that you should probably already know, but you know that the ocean also has variable density. Okay, As you go deeper in depth, the temperature decreases. Okay, that means the density increases. Okay, so on an average, the density, you can say that on an average density is what is a linear function in depth. That means it increases as you go deeper into the ocean. And because there is variable density, there are these waves that form in the interior. Okay, and I'll show you the video before explaining it more. So this is a video around the South China Sea, so which has strong internal waves. So the ocean currents flowing over it, over the hills, and that generates these undulations, which are disturbances or waves that actually propagate outwards from this region, as you'll see soon. So they propagate outwards, and it can go on for even hundreds or even thousands of kilometers, depending on some internal structure of the wave. Okay, and this is something which is not seen by us when we visit the ocean, when we think about the ocean. And these are extremely big, tens of meters of high waves that happen in the interior, unlike the waves in the surface, which are probably meters high, unless there is a tsunami. Okay, so you see that the surface has waves, wind-generated waves that constantly keep on changing. But next time you visit the ocean or think about the ocean, you can also think that the interior is also full of these kind of waves that radiate outwards from their point of generation. Let's say there is these hills and valleys which generate these waves, and they propagate outwards to various distances. So this is so South China Sea is one of the areas where there are strong internal tides. So this is a very small schematic and of how these internal waves or internal tides are generated. So tides and waves are, so tide is a kind of wave in the sense that tide has a certain period, it's a certain time period, whereas waves could be any general disturbance. So as you can see, so there is the interior of the ocean, there is the surface, so there is wind blowing over it, and then it generates, because the wind is blowing, it induces motion, generates internal waves, and this exists only when there is variable density. That means the density is varying, as it always happens in the ocean. And there are different currents, internal currents. For example, as you saw, one of the currents is thermoline circulation that has a deep and surface component. There are various other currents that can happen. And these, when they flow over these hills and valleys, they generate these, again, internal waves that come out. So as we saw in the previous video, they radiate outwards from where they were generated. And they go to far away distances. And these waves can actually break. Okay? So what I mean by breaking is they actually don't preserve their shape, and they will do chaotic motion, and they break, and they generate something called turbulent mixing, so which is again a phenomenon that's related to turbulence. Okay? So they go out, they have energy, so they break, and once they break, if you imagine you are studying tea with your spoon, so you are generating disturbances, so it's mixing the sugar in your tea. Okay? And that's how exactly the same thing happens when a wave breaks. So the waves go away, they break and generate turbulence, they will mix the local quantities. For example, it will mix the temperature, it will mix the salt that's there in the ocean. And actually, there's a combination of surface and the internal things that we have already discussed. So this internal wave has tens of meters of size within the ocean, but on the surface it has only few centimeters of signature. Okay, and the satellites are so powerful that even the centimeter scales of motion can actually be recognized by these satellites. Okay? So if you see something of centimeter scale that's there, that you observe on the ocean, take that something of meters or tens of meters in scale of motion is happening in the interior of the ocean. It's just because of the density differences within this ocean and this ocean versus the atmosphere. Okay. So this is a very simple understanding that you should probably go away with. So all the motions in the interior, all the tidal motions are much higher as compared to what you see in the surface. Okay, so I will go to some very basic fundamentals of fluid mechanics and we'll stop in the next 5 or 10 minutes. But I'll just wait and see if there are any questions regarding what we have discussed, at least in terms of observations, satellite data, mooring, cruises. Yeah. In terms of impact, impact meaning?
Like for example, how have they impacted or what are the results or the destruction they created? Like how big they are in.
Okay, so surface tides are the ones which you observe that's happening on the surface. Internal tides are interior to the ocean. Okay, that's first the difference. And regarding the impact, I am not sure if they have any different impact or they act differently. So they are just different waves that are you see in different. So they are of different length scales, of course. So the way they dissipate energy will certainly be different. But if you see if we humans are impacting it, I don't think. I mean, the only way we can impact it by, let's say, changing temperature, salt concentration. That changes the density. That in turn changes the time period of these motions. But internal tides always remain fixed because they are by the gravitational pull of the sun and the moon. However, because of changing stratification, that means changing temperature and salinity, which changes density, their strength might vary. Okay, so that is how they might be impacted. That's the only thing that I can tell.
In the graph, it showed that salt isn't evenly spread. It is even more than 34% or like that. So why is it?
So nothing is evenly spread. Not even temperature is evenly spread. So there is no homogeneous mixing because there is no steady state. Okay. So there is the salt will so for example, let's go to the Bay of Bengal area. Okay. So Bay of Bengal receives a lot of fresh water. So you know the Indian monsoon, right? In the summer months, we get this huge amount of rainfall that are in the Indian landmass. They go into the ocean. Okay. So these are fresh. Okay. Fresh meaning they have very low concentration of salt. And when they go into the ocean, they reduce your salt concentration. And over time, this fresh water is actually mixed with the already existing salt water, and the density and the salt concentration changes. Okay, so what this was showing you was a very approximate and an average distribution of salt, and so this is not showing you any time evolution of the salt concentration. It's just that on an average, those areas have approximately more than 34 practical salinity units, that's the unit of salt. And the other areas we're showing were fresher, that means they had lesser salinity. As you saw, including the Bay of Bengal and the South China Sea areas, and also in the poles. So you can imagine, in the poles we have lots of ice melting, right? So ice is giving you fresh water, okay? And that goes into the ocean, and that changes the overall salt concentration. If you mix saline water with fresh water, you get something in between. So that is how it's reducing the salt concentration there. Okay, so this is a very average picture. But to give you an estimate, I'll actually show you a video. So I'll stop at that answer. I'll show you a video how in our measurements we are seeing a change in the salinity, and it's not constant. So don't get the wrong picture. It's an average thing. It's an average. It happens something different.
Makes a huge difference.
So yeah, it makes a huge difference because of the fact that because temperature and salt both are changing, it's either increases or decreases the density based on what is the concentration of salt and what is the local temperature. Right? It changes steadily. But I'll show you one measurement from the video. So this is, I'll tell you briefly, very briefly about the basics. So this is a very interesting phenomenon. Yeah.
How much deeper the machines can go to take the samples?
That's a very good question. Anyone have the same question? Did you think about it? So you cannot send everything down below to various steps because of the fact. Sorry. Yeah. So I'll try to give you some kind of an overview. So there is, as you go deeper in depth in water, the water pressure increases, right? And the bottom of the ocean is approximately 300 atmospheres. That means 300 times the current pressure. So you cannot sustain all the equipments. I mean, you cannot sustain every kind of material. So normal material that you send will break under the pressure. I don't know if you have recently heard the news, not recently, probably a year and a half, where there was a submersible which actually broke down, which collapsed with some people inside. Unfortunate incident that happened. So the thing is, if you have to send these instruments deep into the ocean, then it has to be, in almost all cases, made out of titanium. Okay. If it's not, then you can send it to a few meters, few tens of meters, but not deeper than that. So there are various pressure ratings based on the instrument, material, and the quality. And if you send deeper into the ocean, there is a professor who is working on sending submersible into the ocean. So if you go deeper into the ocean, the pressure increases, and there are problems of water leaking into the system, into the electronics. So you have to be very careful about how you design it. Okay. So India has a deep ocean mission, which they are trying to send a round submersible. It's called Matsar. So you can go and check what it is made of. It's made of titanium. So it has a rating of 5,000 meters. That means 5 kilometers. So if you have to send something very deep, it has to be generally titanium. Other than that, you can. So, I think there was a question here. I'll take that first. So is that clear? So it depends on the material.
My question was, during the research, does ocean life interfere with the readings of the instruments, and if yes, how do you tackle it?
Ocean life meaning marine organisms? Yes. That's a good question. So there is a term called biofouling. Okay. So what it does is that because there are organisms which are attracted. So I don't have a picture, but there was an interesting picture which might look ugly to many of you. So if you have these instruments which are fixed for 1 year, 1.5 years, you know there are organisms which are going to be attracted. There are LEs which grow on that. There are organisms which are attracted to eat those LEs, and they actually can contaminate the kind of measurements that you do. Okay. So that's a very good question. It's a problem that can happen in some instruments. There are also ways to clear out those. That's where this is a good question. There are problems. There can be problems. Yeah.
Sir, I wanted to ask that about the flow of the oceans. Does the rotation of the Earth and the torque affect the motion of the oceans at the poles and the equators?
I mean, the poles and the equator thing, but the thing is, if the Earth is rotating, there is always this Coriolis force that acts on influx. Okay, so in the northern hemisphere, there is there's a Coriolis force, and it will always change the direction. And the Coriolis force is a force which acts perpendicular to the direction of the velocity. So if there is a flow in the northern hemisphere, if there is a flow which is going upwards, then you will see that this is deflected to its right. Similarly, if there is in the southern hemisphere, the flow is deflected to its left. Okay, so it's always affecting flows in all the sections of the Earth. Yeah. Okay, so that's a good question. I'll clear some things. So tsunamis are not underwater earthquakes. So these are waves which are generated by underwater earthquakes or any other disturbance. Okay, so it could be, let's say, a huge amount of big iceberg fell into the ocean, which is generating waves. So it's just a wave. It's just another kind of wave, but it's a huge wave of tens of meters of thousands of meters high, not thousands, sorry, hundreds of meters high. And this is a wave which is generated due to disturbance. Okay, so simply speaking, it's a disturbance. Okay, if there is, let's say, you are throwing stone into a pond and you are creating a disturbance. Similarly, if there is something which is happening inside the earth, inside the ocean, which is creating like strong motions, or if there is something which has broken and fallen down into the ocean, for example, a huge iceberg or a piece of mountain, then it can generate these disturbances. And it's actually similar to another kind of wave, but this is it's very destructive because they are very high and they can destroy the coastal areas. Yeah.
So, is there any changes in the tides after some time, or if yes, then how it is affected to marine life?
Okay, that's a good question. So there might have been a slip of tongue. It's not affected by gravitational force of Earth, so it's affected by the gravitational, differential gravitational pull of the sun and the moon. Okay, so it's affected by that, and this actually can change over time, which is of the order of not the given time scale, but the order of that, depending on the relative location of the Earth with respect to the sun, and it can. Well, it's a very speculative question if it affects marine life. I don't know if changing tides can severely impact something, but the thing is, because of changing stratification, changing wave patterns have actually impacted the coral population. But to say whether in thousands of billion year time scale, when the tide changes, if it changes something in the marine life, but yeah, it's a very good research question. I mean, my answer is very vague, it's speculative. I don't really know if there is any such study. Yeah.
So as we have the satellites to measure the waveforms and then how waves, how the tide, especially tidal waves flow in the ocean in a particular arrangement, is there a way to predict that this will, the upcoming catastrophe that will going to happen in the near future? Is there a particular way to observe the patterns and later work on it?
There is a way. I mean, people do predictive modeling. Okay, so that means you understand, you know what is happening in the oceans now. You have the data, and you have numerical, you have computers. You have strong computers to understand those things. I mean, to understand an ocean. And people do those, we call it simulations. That means you simulate the ocean. So you are trying to understand it from a computational perspective in your lab. So you're running it, and then you see what is happening later on, let's say hundreds or thousands of years or a million years from now. Whereas this is good to do that, but there are certain problems. The system is actually something called non-linear, in the sense that you'll probably understand in your higher classes. if you have, so there is no equation that can give you the answer at all times, okay? And it's very sensitive to the initial conditions. So let's say you do something wrong in your initial conditions because of your measurement error or because of your computational mistakes, simulation mistakes. You will end up something which is probably not real. However, I'll give you just an addition to that. So this is always a fault in all the numerical simulations that people do for long term. So you cannot really predict what is going to exactly happen on, let's say, on the year 2100 on 15th of July. Let's say no one can actually predict it. Okay. However, when you run these models, one of the most common themes that actually comes out of these computer simulations is that the Earth is warming, and there is global warming the Earth will change because if we continue doing the trends we have. But we can only say about the trends. We cannot really predict what exactly happens on a certain day because the system is non-linear and it's very complex. So I'll briefly again go through the basics. We'll stop in 5 minutes. I just wanted to give you an idea of what is happening in the atmosphere is also observable in the lab. Okay, so these are two different pictures. So this is these are images of clouds in Wyoming. So Wyoming is in which country? In the US. So it's a state in the US, and you can see that there are these structures which are forming, and similar structures have been reproduced in lab experiments, which are of this scale, okay, meter scale, and there are similar patterns that actually can you can reproduce it from lab and see those things in certain conditions in the atmosphere. Okay, so these features are called there's a term called the Kelvin-Helmholtz billows, and these rise because there is an instability in the flow. And these are some of the people who actually tried to study understand the equations of the actually try to understand the governing equations which try to go or how those how they modify the different forces. So starting with Leonhard Euler, he had a research paper. So it's actually one space law. So it was a research paper. So research papers are something where you write a certain finding. Okay, so you do some work in your lab or a computer, and then you write about the findings, and then you send it to the people who are expert in your fields to read that, and then you publish in some kind of a journal, okay, some magazines. So he had a paper in 1755, which actually gave you a brief understanding of how the flows evolve with respect to forces. Whereas, you can imagine this was 1755, he didn't have everything to do it. So some experiments failed to match the equation that he gave. And there were people, one of the first people, he was the first person in 1822 to write a paper. He did some calculations. And he gave us this most famous form of the equation that governs the fluid flow. And this is a combination of their names. So this is Claude Navier and George Gabriel Stokes, and this is called the Navier-Stokes equation. I'll show you this equation and we'll stop here. So Euler actually got only up to this, whereas this term was introduced by Claude Navier, and then there were some experiments which were done 30, 40 years later by Gabriel Stokes, and actually this is still called the Navier-Stokes equation. And so just to give you a hint of the variables here, so there are velocities, that means the velocity is the flow, and this is the, there are forces that are occurring, so there is a pressure force which is changing the velocity field, and what the thing that Euler actually missed its calculation is the term which is here, and this is representative of the thing called viscosity. Okay, so if I give you an example of honey versus liquid water, which do you think is highly viscous? Honey. So it's a resistance to flow. It's a force which prevents motion of different layers of fluid. So he missed the calculation, Euler missed the calculation, and Navier did that, and Stokes further worked on it. And this is one of the, so we stop with that statement, this is one of the most, one of the unsolved problems in classical mechanics. This is one of the 7 unsolved problems by this institute called the Clay Institute, the Clay Mathematics Institute. So they have 7 problems which are incredibly hard to solve, and only one of them has been solved. And then Navier's rules, which, I mean, there's a problem statement, you can go and look into it if you're interested. There's a problem statement that tries and asks people to prove the existence and uniqueness of the solutions of the Navier's rules in 3 dimensions. So this governs free flow, and this is one of the most important unsolved problems in classical mechanics. And there's a $1 million prize for a person who solves it first. So this is where we stop. We are going to the basics, and then we saw that this is the equation that governs the fluid flow. And I will take questions, and we'll probably not discuss further in the slides. Is there another question? Yeah.
Good morning, sir. So, you told us about the geographical aspect of fluid dynamics.
Yeah.
I would like to know that if there is a scope of research in the field of fluid dynamics, but in terms of physics, not like on the aspect of geography, but as in classical physics, is there anything left to be researched in fluid dynamics?
Well, I just gave you one of the most open problems in classical fluid mechanics, classical physics. So this is a $1 million prize, and this is the turbulence is the unsolved problem. Many people have worked on it, including the giants like Euler, Navier, then Stokes, and then Cauchy, Boza, G.I. Taylor, Batchelor. These people have worked on it for hundreds of years almost. And this is an open problem, and this is being dealt by various communities. Okay, so engineers are interested in trying to understand turbulence because they want to reduce drag on planes that move, which can save you millions and millions of dollars, and also reduce gas consumption, fuel consumption, which is planet sensitive. Physicists are trying to understand the fundamental aspects of turbulence. Why does it happen? What are the characteristics? And every single day, every single month, they keep on cracking up their computer simulations that we are talking about. So they solve this equation. Okay, so this is not one equation. These are 3 equations because the velocity has 3 components. U, V, and W. So that's why it's called the Navier-Stokes equations. So it's 3 equations. So they solve the equation using various numerical techniques that you probably understand as student. So they solve it in computers and they understand their properties. So so this whole field of how something from organized to disorganized happens. Okay, there's a transition. So if you imagine, so you might have seen incense stick, right? So when you burn an incense stick, initially the flow is very organized, and then suddenly it starts something, and then it starts making these whirls, and then it dissipates, right? So that means there's a laminar flow and there is a turbulent flow beyond it. But why does it happen? I mean, what's the reason for that thing to happen? So there is a strong area of research in the small region where the transition from laminar to turbulence happens, and what is the property of turbulence? Actually, I mean, just from physics, from mathematics, from engineer's point of view, and various others. I mean, it's still an open question. It's literally a $1 million problem. So,
and sir, I have one more doubt. I found this equation very similar to the Schrödinger wave equation. In that equation, I can understand that it's the second partial derivative of the wave function with respect to its coordinate.
yeah.
So, in this equation, can you explain the various terms in this equation?
Yeah, certainly I can explain the various terms. So this is giving you, first of all, this du by dt. So that's the first is giving you the partial derivative of the velocity field with respect to time. This u dot grad u is a non-linear term, so probably you have not heard of grad, at least most of you. So this lambda operator is a del operator. So u dot grad u has the form of something like this. So this is a non-linear term which actually creates all the trouble in solving the Navier-Stokes equation. So this is the del operator, and this has the form of del del x I cap plus del del y j cap plus del del z. So if you don't understand, don't worry. At least like someone of you interested, you can go and look at this del operator. So this is a vector operator, and there is a velocity field which is u equal to let's say there's a u vector ui cap plus bj cap plus wj cap, where if you understand this from your wave equation, you know that these are the unit vectors in the x, y, and z direction, these are the components. So you do a u dot grad u, and this gives you an advection of the velocity by the velocity itself. Okay? So u dot grad is an operator which acts on the velocity field, and then it gives you the advection of the velocity field by the velocity field itself. So that means it's a non-linear term. And this one is modified pressure, where it tells you that this flow is being driven by some kind of a gradient. Okay, there cannot be any flow if there is no force, right? It means, yeah.
Pressure was scalar quantity. Pressure was scalar.
Yeah.
So, but this operator,
Yeah.
the delta, it basically gives the unit vectors. It partially differentiates it with the I vector, J vector, K vector. So, wouldn't the
Yeah, so we'll stop it here. So this is a good question. This is pressure is always scalar, and del P means del P del x, del P del y, del P del z with respect, and it makes the vector. So this is a vector equation. This is a vector, this is a vector, this has to be a vector. It will always scalar. So del operator acts on the pressure to give you the changes in pressure in each direction. And then this del dot P is actually, this whole term is vector. It is the pressure, but you can of course operate the pressure on the del vector to get this. So we'll stop at this.
Okay, so thanks a lot. So like always, the questions are unstoppable, so I have to intervene and stop it. But you can, of course, continue asking questions. Please catch him later, after the session is finished, outside, and I hope he's okay answering more of your questions, okay, in more details. So let's thank Professor Yeah, I hope all of you had a good time. So now we'll have a photo session, right? Yeah, here. So everyone please gather over here before dispersing. We'll have a group photo. Okay, so before the photo, we would like to have feedback from you about this session and about your experience in the Sci-Tech. Okay, so it won't take long, just scan this QR code and please give your feedback.
Students, all of you are required to give your feedback. Please scan the code now. And then